my name is Tianhan. Today I will talk about our work Selectively-Amortized resource bounding. What is resource bounding? By resource bounding, I mean when given a bound, we want to statically and automatically verify this bound on the resource usage of a program, which is accumulated over time. Let's next understand why do we need to bound resources. You may care about resource bounding as it provides valuable insights on software performance such as time and memory usage. If you are developing security-critical software, resource usage may be connected to, for example, denial of service vulnerabilities. Finally, in some of more modern applications, resources may have direct economic impact such as gas costs for smart contracts in cryptocurrency. To be concrete about the resource bounding problem that we address, let's look at an example. Our example is to flatten a list of words and then copy the flattened text n times, which we can see as a simplified model of outputting n database queries. The resource that we are interested in is the number of characters in the result. Source is a list of words. Dest is a result string. We first flatten list source, then we copy the flattened list of text for n times. The resource of interest here is the number of characters in string dest. Since list source is copied n times, we want to verify that it is valid for any reachable program state that the number of characters in dest or the number of copied characters is no greater than n times the number of characters in source. Since we are only care about the number of characters of dest, we consider a numerical resource abstraction of this flattening routine with the changes in the length of dest. We present the number of characters in source and dest by integer typed variables with the same names. For example, source represents number of characters in the source list. We first assume n is non-negative. Then, the outer for loop iterates for n times, which means copy for n times. Then, at the beginning of every outer loop iteration, variable remaining, which means the number of characters that remain to be copied, is initialized as the number of characters in source. Then, as long as variable remaining is positive, we decrease it by some non-deterministic positive amount, word. Word is the number of characters in a word. Words may have different sizes. This is achieved by non-deterministic star assignment and the assume command. Finally, copying a word is realized by a special command called use. Use command generically expresses resource consumption. This command takes two arguments, dest and word. Dest is a resource that we are interested in, tracking the total number of characters that have been copied. Word is the amount of update in dest. In other words, the semantics of this use command is to increase variable dest by the value of word. Now, the goal is to verify that this bound assertion is valid. Dest is no greater than n times source. To verify this bound assertion, let's first look at a most intuitive and simplistic approach. We first consider the use command always has worst case cost whenever executed, which is source, because a word is at most as large as the entire source. Second, we analyze how many times this use command can be executed. Lastly, we approximate the value of dest by multiplying the worst case cost per word, which is source, with the max number of times executing the use command. Can we verify the given assertion by this approach? No. The key reason is that the max number of times executing the use command is n times source, because each inner loop iteration decreases remaining by at least 1. With n times source, we can only verify a weaker upper bound, source times n times source, instead of the desired bound, n times source. Now, the key question is, why does this approach fail to provide sufficient precision? The reason is that although the length of words may vary, which is exemplified by this figure where numbers represent the length of words, this approach assumes each word to be at their maximum length. Let's give this approach a name, worst case reasoning, because it considers each operation to always consume a worst case amount of resources. For example, worst case execution time analysis and reachability bound analysis both adopt this reasoning style. Now, how to fix this imprecision? Instead of assuming every word has a maximum length, we want to precisely consider the variations in the length of words. That is, we want to consider the techniques that can account for its variations, where low usage in one iteration amortizes for high usage in another, or vice versa. Now, let's consider amortized reasoning, how it works on our example. We can get amortized reasoning by inferring inductive invariants for the program. In particular, this inductive invariant, right before the assertion, is sufficiently precise for verifying our bound assertion. It says the sum between what has been copied, which is dest, and what remains to be copied in the current iteration, which is remaining, is no greater than I plus 1 copies of list source. However, this inductive variant is hard to infer because it involves an arbitrary polynomial among program variables. It is generally non-trivial to infer such invariants, and thus it's brittle to automate. To summarize, so far we have introduced two approaches. Worst-case reasoning is simple, but it is not precise enough. Amortized reasoning is precise enough, yet it is highly complicated. Wouldn't it be great if there exists an approach that is both simple and precise? Wouldn't it be even more great if we can arbitrarily adjust the simplicity and precision? This is exactly our contribution. We managed to get both precision and simplicity by introducing selectively amortized reasoning. To achieve this, we rely on a key technical concept called amortization segments as a parameter to our analysis. We also prove arbitrary selectively amortized reasoning is sound to over-approximate the resource usage. Finally, we define non-interfering amortization segments so that we can design an algorithm to automatically select an amortization strategy. Let me now introduce selectively amortized reasoning. The key novel concept in our approach is what we call amortization segments, which is a range in the program execution where we apply amortized reasoning. Here, we use a red box to informally indicate amortization segments, which consist of a single iteration of the outer loop. This segment amortizes uses for dest over all iterations of the inner loop. The key idea is to apply amortized reasoning within segments, which we have just introduced, and then apply worst-case reasoning over segments. The result is this approximation of dest. This inequality means the worst-case cost of executing a segment is source, because one iteration of the outer loop copies the entire list source. To obtain this estimation, we must apply amortized reasoning within the segment, because the lengths of words may vary. Then, we analyze the max amount of times the segments can be executed, which is n, because the outer loop iterates for n times. Thus, this product is using worst-case reasoning, because it uses worst-case cost of any segment, which is source. While here we visually illustrate segments as a code block, we actually define segments as a partitioning of program traces. Consider an arbitrary program trace. We visualize its accumulated resource usage by this graph. X-axis is time. Y-axis is the accumulated resource usage. Then we partition the accumulated resource usage into segments. The height of the segment represents the accumulated resource usage in the segment. The bottom box, or the first segment, accumulates R1 amount of resources, and the top box, or the current partial segment, accumulates Rk plus 1 amount of resources. The key idea in selectively amortized reasoning is to soundly approximate the actual cost by first approximating the last segment with its exact cost, Rk plus 1. Then we approximate every other segment with a cost of R star. R star is the max cost among all segments from R1 to Rk. Mathematically, we approximate the actual cost in a program trace, which is the right-hand side of this inequality, the sum from R1 to Rk plus 1, by the left-hand side. On the left-hand side, we first multiply the number of segments, which is k, with the max cost among all segments, which is R star. Then we add the cost of the current partial segment, Rk plus 1. Importantly, this is not only an inductive invariant, but also an inductive invariant that holds true no matter how we select segments. Because in this approximation, we do not have any assumption about segments. So far, we have introduced selectively amortized reasoning and informally given a sense of why arbitrary selective amortization is sound. Since now arbitrary choice of segment is sound, the next natural question is, how do we actually select a segment? Back to our visualization of selectively amortized reasoning. We partition program trace into a sequence of segments. R1 through Rk plus 1 represents the amount of accumulated resource usage in the segment. On the left, R star is an approximation of R1 through Rk. Recall that R star is a max value between R1 through Rk. Now the question is, when does the approximation on the left precisely describe the actual cost on the right? The answer is when every 2 rounds of the segment have the same resource use. The reason is that if R1 through Rk are all the same, then R star is the same as R1, R2, and all the way up to Rk. And therefore, the approximation on the left is exactly the same as the actual cost on the right. This is our guiding principle for automatically selecting the amortization strategy. We do not want to lose any precision. Now, how do we find the segment decomposition such that any 2 rounds of segment have the same resource use? Back to our example. Let's consider 2 rounds within the segment. What we care about is the value of the resource variable dest when exiting the segment, the output of the segment. Dest depends on word, remaining, and source. But for this segment decomposition, we see that source is the only input variable. So for any 2 rounds through that segment, as long as source is the same, dest will be the same. Since we can prove that source is the same on input whenever we enter this segment decomposition is precise. Or we say that this resource used in this segment decomposition is non-interfering by analogy to non-interference in security analysis. Algorithmically, we want to find the smallest non-interfering segment decomposition to minimize this precise but complex, brittle, and expensive amortized reasoning. We implemented this particular amortization strategy in our experimental evaluation. We considered the research question about whether selective amortization can improve the number of verified assertions when compared with the 2 extremes. We consider examples extracted from 4 Java libraries, plus a set of randomly generated examples based on Java loop idioms. We consider the number of proved bound assertions using the 3 configurations, worst case, fully amortized, selectively amortized reasoning to try to prove the most precise bound. Then, we use another set where bound assertions are slightly weaker. We highlight the configurations that proves the most in each category, which provides evidence that selective amortization overcomes some imprecision of worst-case reasoning by proving more bound assertions. Meanwhile, selectively amortization also reduces some complexity compared with fully amortized reasoning. Although fully amortized reasoning is theoretically more precise, it sometimes proved less bound assertions because its high complexity makes it more brittle. To conclude, in this work, we introduce selectively amortized reasoning. For this example, selectively amortized reasoning could mean treating one iteration of the auto loop as a segment. By contrast, worst-case reasoning treats a single use command as a segment. It is simple because it considers every use command to have a worst-case cost. Amortized reasoning treats the whole program as a segment. It is precise because it infers invariants for the entire program. By parameterizing analysis with segments, selectively amortized reasoning can get precision when necessary and simplicity when possible. At one extreme, worst-case reasoning emphasizes simplicity at the cost of imprecision. At another extreme, amortized reasoning emphasizes precision at the cost of complexity and brittleness. We opened up a new space by allowing choosing arbitrary point on this axis. With that, I'm happy to take questions.